All right. Okay, week 9 of emergence and phase transitions. So next 4 lectures are going to be really great. What we're going to be doing today is we're going to be starting the field theoretic version of the normalization group, but I'm not going to do it in all the details and so on and so forth. You'll get enough of it that you'll understand the basic idea, and you'll see how it maps onto what we've already done in the real space. So what I'm going to do today is we're going to talk about Landau theory, and I'm going to show you how to write Landau theory, write the partition function as a path integral, which we'll explain what that is, as you know, and then we'll use dimensional analysis to solve the problem. Why is it that there isn't a small parameter in phase transitions? So you'd think that there would be. You would say we're close to TC. T minus TC over TC. It's got to be a number that's 0.01 or something like this. We've got a small parameter. Hallelujah. Perturbation theory. Okay? It doesn't work. Okay? And the reason it doesn't work, we can understand that by doing a dimensional analysis. So we're going to do that. And then once we've realized that everything is messed up, then we're going to start talking about how we go back to using renormalization group concepts to then start evaluating the partition function using field theory, which basically means doing what we were doing last week, but doing it in momentum space. Okay, so let's jump in. So we're going to be following, for now, Landau theory and dimensional analysis. And you can find this in my book in chapter 7. When I was writing my book, I gave it to a number of people to read, and the unanimous consent was just the one chapter 7 made the book worthwhile. So it's very simple, but these things aren't, at least at the time when I wrote it, weren't really explained. So here's what we're going to do. We're going to start off with Landau theory. So I'm going to write down the Landau theory for an order parameter, which I'll call S of R. And we've constructed that in the past. So let's write it down. I'm going to be in D dimensions. So I'm integrating over the gradient term, which I'm going to write as 1/2 grad S squared, and then the uniform free energy density, 1/2 R0 squared plus 1/4 U0 S⁴, and then a coupling to the field. So I'll call that H0 times S. And I've used units here. Actually, why have I used units here? Yeah, I've used units here, which are as follows. Here I've defined S of R to be beta times gamma to the 1/2 times the magnetization. And I'm going to put here a little lambda on the S to remind you that this is a coarse-grained variable, and so it doesn't really have Fourier components at long wavelengths, at a large k larger than this cutoff. And then this R0 is what I called a T, where T is T minus TC over TC. And this U0 over 4, that's what I previously called B. In fact, if you look at the way I normalize things, it's B over beta times gamma squared. So that's the mapping between the form of the Landau free energy we wrote out with coefficients telling you, gamma tells you how much energy cost there is to a gradient in the order parameter profile. So that's the energy cost that penalizes departures from uniformity. Beta is 1 over kT, and then there's the quadratic term, which is proportional to how far you are away from TC, and then there's the quartic term, with just some constant number, which I called previously b, and so I've rescaled everything in these units. So this is the we can think of this as being a we've made some form of redefined order parameter, and I've written it in this way. I've chosen these parameters so that the coefficient of the grad s squared term is just 1/2. When we did this originally, when we derived this, there was a factor of gamma in there and so on, and so we've chosen units where that coefficient is just 1/2. So that's the partition function, and I'm going to write this as, I'm going to call this thing the effective Hamiltonian. So I'm going to write this as H effective S like that, and then if I want to compute anything, what I have to do is compute the partition function. So the partition function is just Z is the trace over all my coarse-grained degrees of freedom, S of R, and then e to the minus h effective as a functional, I should say, of S of R. So that's the problem, and we haven't really been very precise about what we mean by this this trace operation here. So I've told you before, and we've seen that this is really just an integral, a multiple integral over Fourier components with k greater than lambda. And I just want to just check, am I defining lambda in real space? Yeah, so. So I'm only integrating over long wavelength components like that. Okay, so that's the problem, and so what I want to do now is the goal of this section is do a dimensional analysis of this field theory. So we call this a field theory because S is just a function of space. It's a continuous function in space. It's smooth. It's coarse-grained, so it's smooth, and we're averaging over all the statistical fluctuations of this field. So when we do this trace, what we're doing is we're averaging over all the statistical thermal fluctuations of S of R, and that's why we call this a field theory. Okay, what page number am I on? Page 176. There we go. All right, so let me leave that there, and we'll switch over here to page 177. Okay, so goal is dimensional analysis. So step one, how do we do dimensional analysis? Especially since I've redefined the variable in some very sneaky way. So the main thing is that the first thing is that we note that we have H effective of S is in an exponential. We've rescaled out KT. And so it's just H in the exponential. And if it's in the exponential, it must be dimensionless. So if I want to work out the dimensions of the effective Hamiltonian, those dimensions are equal to 1. Now, the effective Hamiltonian is a sum of all the various terms. and all these terms must therefore have the same dimension. So let's have a look at the first term. So that's the first thing. So step one is that. Step two, we're going to figure out the dimension of the field. So how do we do that? Well, what we do is we look at the first term in the Landau free energy, and so what we know is that the first term, integral d dr of 1/2 grad s squared. So this thing must have dimensions of 1. Okay, but what about the other terms in here? Well, this thing over here, this is ddr, so this has dimensions of length to the power d. The gradient term, that has dimensions of length to the -2. Well, each grad operator is length to the -1, but with it squared, so that gives you L to the -2. And then we have s squared, whatever the dimensions of s are. So we have this times this is equal to 1. And so now we can then read off that the dimensions of this field are L to the power 1 minus d over 2. Okay. So that's the formal dimension in these units of the field itself. Okay, so now let's have a look at the next term. So step 3, let's look at the third term, the second term in the equation. So now we look at R naught. What is its dimensions? And so we do the same trick. So we now know that we have the integral d dr of R naught times s squared, and that thing, the dimensions of this are equal to 1. Okay, well, so this thing again, this is L to the d. This thing over here is L to the 1 minus d over 2, and then squared. And then this thing over here is the dimensions of R naught. And so that tells us that the dimensions of R naught, if I did this right, are just length to the -2. Okay, so that's interesting, because you could have expected this. So here's a comment that we can make. So the comment is this: we know that the length is going to scale something like the correlation length using that kind of argument. And we know that the correlation length scales like t to the -1/2, at least in mean field theory. So what that then tells us is that R naught is proportional to t. And that's exactly what we already know, because we already know that the coefficient of the quadratic term is proportional to t minus tc. So in other words, this is consistent with the coefficient of s squared in the Landau free energy is proportional to t minus tc over tc, so which we already knew. And remember, that term was just tm squared or ts squared. So everything we've just done with the dimensional analysis are confirmed. So that's step 3. Now let's do step 4. So now we're going to look at the dimensions of U naught. So we do the same trick. So we say, well, I've got to look at the dimensions of the integral ddr U naught s to the 4, and it sounds like the aliens are landing in the front of UCSD there. Thanks. Thank you. Okay, so that is equal to 1. And so so this then tells us that so we have integral of u naught, then we have L to the D, and then we have L to the 1 minus D over 2 raised to the 4th power. And so that's going to tell us that u naught actually is going to go like L to the power D minus 4. Okay, right. Now, remember what we just said. The characteristic length scale here is L, which is the correlation length. And the correlation length in mean field theory goes like T to the minus 1/2. And so what that then implies is that u naught itself is going to scale like T to the minus 4 minus D divided by 2. Okay, so I'm using mean field theory here because Landau theory is mean field theory. So what we're doing now is we're looking to see, we're in mean field theory, so we're using the mean field theory exponents. So if u goes as T to the minus 4 minus D over 2, let's set D equals 3, for example. And that says that u naught scales like T to the minus 4 minus 3 is 1, minus 1 over 2. And so what that means is that when I take the limit as T goes to 0, u naught actually goes to infinity. So this is bad news, okay? Because u naught describes the interactions of the field with itself. And so what we've just said then is that the interactions become very important as T tends to 0. In other words, T is tending towards Tc. The quadratic term stays small. And so this problem is dominated by strong interaction. As T tends to Tc. And so what that basically means is that we don't have a usable small parameter. And that's the big surprise. That's the thing that made this problem unsolvable for more than 50 years. Okay, so that's the first part. So this tells us then that something interesting is happening. So our conclusion, we can be a little bit more precise. The conclusion is 1, if D is less than 4, then as T goes to Tc, the interactions get stronger and stronger. And that means that we can't use perturbation theory. So that's that. On the other hand, it does tell us that if D is greater than 4, then that means that the interactions get weaker. And so and in fact they get weaker and go to 0. And so that means that mean field theory will be fine. And so we've just deduced then that DC is 4 is the upper critical dimension. So in other words, if you want to look for a small parameter, you're not going to find it in the strength of interactions. The only small parameter that we have is how far away you are from 4 dimensions. So we have to do an expansion in dimension. Okay, so that's the first thing that we've learned, and this is why the problem is hard. So now I want to talk about the basic idea of doing a renormalization group. So and we are going to come back to dimensional analysis a little bit later. So now I want to talk about the basic idea of the sort of field theoretic RG, at least in the Wilson framework. And so I'm copying now chapter 9. So what is the basic idea? So the basic idea is that instead of computing block spins in real space, what we're going to do is, and so when you compute block spins in real space, what you're doing is you're eliminating the small wavelength, small distance behavior. So instead of doing that, what we're going to do is integrate out Fourier components with wave numbers k greater than 2 pi over lambda. So actually, I'm going to define it the other way around. I'm going to define it to be k greater than lambda, so I don't have to keep writing down 2 pi's over lambda. So we're going to integrate our Fourier components with k greater than lambda, and then that's going to give us not block spins, turn into effective long wavelength degrees of freedom, wavelength Fourier components. So what I'm saying then is that we're going to start off with S lambda of R. We're going to write those as Fourier components. I'll try to remember to put a hat here. And then this thing will only have naught is less than k is less than lambda. And what we're going to do is we're going to integrate out the k greater than lambda. So we eliminate those. So in other words, the way we get block spins, what we're effectively doing is we're going to rescale by a factor of L and eliminate, if you like, integrate out lambda over L is less than K is less than lambda, like that. And so where we did a block spin, where we made a block of size L in the lattice space units, and then integrated out the degrees of freedom smaller than the block, and then got an effective description for the block. Now what we're going to do is we're going to think of our block as being, we're going to change K from K to K over L. So we're going to make the K smaller. We're going to look for smaller values of K, which means longer wavelengths, which is exactly what a block is. And then we're going to integrate out the degrees of freedom that we don't want. So this is the this is sort of, if you like, following the Kondo strategy. So the Kondo strategy is to take anything that doesn't spark joy and throw it out. Okay, so the Fourier components that are at high wave numbers, we don't want those, so we throw those out, and so we get a new kind of renormalization group. So what we're going to end up with is that we're going to have renormalization group recursion relations for R naught and U naught, and those are going to be the coupling constants. Okay, so we've talked about that. Then I want to just repeat again about the epsilon expansion. So this was due to Wilson and Fisher. This paper from 1972. And so we're going to, so their paper was actually called Critical Phenomena in 3.99 dimensions. So we're going to literally compute critical exponents in terms of epsilon. And then in real life, we live in 3 dimensions. So what you actually want is to set epsilon, which is 4 minus d, set that equal to 1. So that gives you the behavior for d equals 3. And you may say, well, if you do this calculation, you do an expansion, perturbation theory in epsilon. Epsilon is small. And then you say, okay, actually, we've done the calculation now, but epsilon is going to be 1. Then you think, well, people are going to just laugh at you and throw eggs at you and stuff like this. Well, they won't throw eggs at you because they're too expensive. They'll throw tomatoes or something like this. Okay, but it turns out you can use advanced mathematical techniques like Borel summation and other techniques to take a series that you calculate in epsilon and then resum it so that it actually gives you good results, even when epsilon is equal to 1. Okay, so there's applied mathematics techniques for doing that, and there's a whole theory to do that. So let me just record that even though we do perturbation theory in epsilon, we can use Borel summation and other methods to extrapolate perturbation theory to epsilon equals 1. Okay, so what we're going to end up with is a power series is in epsilon, and then what we know is, well, above for d greater than 4, we know that the Gaussian theory should work fine. And so what we would expect is that we will find that R star, U star, H star, all of those things are actually going to be equal to 0, because by definition, that's when R is proportional to T minus TC. U will go to 0 if you're above 4 dimensions. The external magnetic field must be set to be 0 in order to get a critical point. And so this should be a Gaussian functional integral of L is just the integral of d dr 1/2 grad s squared plus 1/2 r naught s squared, and this thing we can do exactly, because it's only it's a quadratic form in an exponential, and we know how to do Gaussian integrals, and you've done them in the homework, so you know how to do them. Okay. Okay, so that's true for d greater than 4. For d less than 4, we're going to find that there is another fixed point, which is called the Wilson-Fisher fixed point. And we expect it to be of order epsilon away from the Gaussian fixed point. So why do we expect that? Well, let me give you a plausibility argument. So our plausibility argument, it goes like this. We know that U goes like, has dimensions L to the power 4 minus D. So let's suppose I start off with some quartic coupling constant U0, and I do a renormalization group transformation by a scale L. So then what's going to happen is U0 is going to go to a new coupling constant, U prime, and that we would expect to go as L to the power 4 minus D times U0. Okay, because of the dimensions. Okay, well I can write this then as L to the power epsilon times U0. So remember we talked about the differential renormalization group a week or two ago. So if I were to write this in differential form, so I would say let's define S to be the logarithm of L. So if I make that definition, then I can write the recursion relation in differential form. In other words, for infinitesimally small L. So that would then be that du as a function of scale will then go like epsilon to epsilon times u. So basically this says if I change my scale by s, which is log L, then u will change by epsilon times u, and the solution of this equation is that u scales like L to the epsilon times u. So this is equivalent to this statement here. Okay, now this would be true if dimensional analysis just persisted all the time. But now what happens when you do integration out of the small wavelength degrees of freedom? So when we integrate out the k is greater than lambda over L, those long wavelengths, the small wavelength degrees of freedom. When we integrate them out, that's going to introduce new couplings, just as we saw with the real space renormalization group. And so it's probably not a stretch of your imagination to guess that what we would see then is that du at the scale s by ds is going to go like epsilon times us, which is what we got from mean field theory. But now we would say, well, there's going to be another term here, and I'm going to write it as some coefficient times u s squared, and there'll be higher order terms. Higher order terms induced by renormalization group. So that's plausible. I haven't calculated it yet, but it's plausible that when you do integration out, you change the coupling constant, so the recursion relations change, the renormalization group flows change, and so we will get these extra terms as shown over here. So let's suppose that that's true, which in fact it is, and we'll calculate that. Then when you look at the fixed point, the fixed point is when du by ds is equal to 0, and you can see then that tells you that u as star is going to be epsilon divided by this coefficient a. And so it tells you that if this is what happens, then there'll be a renormalization group fixed point at order epsilon away from u equals 0. And so there'll be a non-trivial fixed point with its own eigenvalues and eigenfunctions and eigendirections and the associated critical exponents. So what that means is that our goal should be to compute this precisely and consistently order epsilon, and then once we've done that, compute the linearized renormalization group transformation. Near this fixed point, and then get the eigenvalues, and from that get the critical exponents to. So that's our plan, and that's what we're going to do. Okay, so to get started on that, the first thing I'm going to do now is I'm going to compute the functional integral for the Gaussian model first. So the strategy is going to be first study the Gaussian model, which we know is okay for d greater than 4, and use that so that we really understand what we mean by functional integration. So we're going to understand functional integration, and we're going to do everything by analogy with what we did in real space. I'm even going to use the same notation for the small scale variables and so on, so that you can see the exact analogy. Okay, so that's what we're going to do first. And then once we've done that, then we're going to, so that's the first thing. And the second thing that we're going to do is then compute the full Landau theory renormalization group. Okay, so any questions about where we're going before I get into the details of the calculation? So the first calculation we're going to do is going to be quite simple. And then the second one is going to be more involved, but I'm going to skip all the details and just tell you the final answer, because it's not important that you know the precise tricks and so on you need to do to evaluate the Feynman diagrams and compute all the combinatorics and so on. Okay, all right, so go ahead. Yep, okay. So let's start off then with the Gaussian model. So I'm going to write the effective Hamiltonian is the integral dr of 1/2 grad s squared plus 1/2 r naught s squared. Okay, so that's my theory. So now I'm going to write down Fourier transforms. And I want to make sure that you know how to define the Fourier transform properly. So this is discussed on page 155 of my book, the lecture notes. And I'm going to just quickly go through that just to make sure that you understand how one sort of understands how one gets your Fourier transform algebra correct. So what we're going to say is, if I have a system in a volume V, then I can write my S of R as 1 over V times the sum over the Fourier components S of K e to the I k dot R. So that's the Fourier transform. And the Fourier components themselves are written as the integral ddr over the volume V of S of R e to the minus I k dot R. So that's my definition of Fourier transform. Okay. Now, one thing it's important to do whenever you can define Fourier transforms any way you like. However you choose to do it, you want to make sure that it's consistent. And so how do you, because you never remember, there are the factors of square root of 2 and stuff like that, factors of V, there's many different ways you can define it. So the next thing you want to check is what's called the resolution of unity. So what do I mean by that? So suppose I take my formula for S of V, so for S of K, and I plug that in to my formula for S of R. Okay, so here I've got S of K. I'm going to put that into here, and then what I should get on the left-hand side is S of R, and on the right I should get S of R. But I'm not going to get S of R, I'm going to get a big mess. And that thing must be S of R. So let's just see how that works. So what happens is I can say that S of R is equal to 1 over V, the sum over K, e to the I K dot R. And then I've got to put in S of K. So now I put in S of K. So S of K is 1, sorry, it's not that. S of K is the integral over V d R S of R e to the minus I K dot R. Right? 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 No. No. I tricked you. It's not right. What's wrong with it? Great. We have, this is a dummy variable. This is a dummy variable. So this thing is a dummy variable. So it's not the same thing. Okay. So then I can say then that this thing should equal the integral dd r prime S of R prime times stuff. So let's write down what the stuff is. So the stuff that is in there is 1 over V, the sum over K, e to the I K dot R minus R prime. Okay, so let's just see where all those bits came from. So this bit over here is just this. Okay, then all of the other stuff that came from here and here, and those things have gone into this part over here. And we know that this thing has got to equal whatever it is on the left-hand side. So we know that this thing is equal to the integral d r prime s of r prime times the only thing that can make this magic happen, the left-hand side equal the right-hand side, if this thing over here is delta of r minus r prime. And so what we've learned from this exercise is that the expression 1 over v sum over k e to the I k dot r minus r prime is equal to delta of r minus r prime. And remember, r is a variable in continuous space, but it's continuous space in a finite volume. So the allowed k modes are like 2 pi over the cube root of v, or the dth root of v, times integers. Okay, so r is continuous in some space volume v. K are discrete. So, k is like 2 pi over v to the 1 over d, and then k1, k2, k3 up to kd. So the k vectors are quantized. And so when you sum over those quantized ones of that thing, actually you get the Dirac delta function. Okay, so you've seen that before. Okay, and then we can check that this makes sense. So how do we check that? So let's check that this makes sense. Well, so this sum over k, this sum over k here on the left-hand side, whenever you have a sum over k, as I take the system size going to infinity, then the sum over k is going to go to some integral dk, right? Oops, not dr, dk, something like that, okay? But there's going to be a factor that goes in front there. And there's a factor that goes in here because this is dimensionless. And then this thing here has dimensions of k to the d. And so this thing over here is called the density of states in k space. And it's the first order term that converts a sum over k into an integral over k. And since we know that k goes like 2 pi over v to the 1 over d, k1, k2 up to kd, so you can see that the sum over k, which means the sum over k1, say kx, sum over ky, or k2, sum over kz. If you're in 3 dimensions, maybe if you're in d dimensions, the sum over k to the d. So this term over here, the Jacobian of this transformation, the Jacobian of going from integers to k is, well, I've got k. Let me just do it in 3 dimensions. So I got kx. Well, it's not kx, ky, kz. It's actually integers nx, ny, nz. These things are integers. And so dk is equal to 2 pi over L to the d times d of n. And these things are all 1 because you have integers. And so what you then get is that the density of states in k space that converts a sum over n to an integral is just L to the d over 2 pi to the d, in other words, v over 2 pi to the d. So now let's see if that works. So then I've got 1 over v sum over k e to the I k dot r minus r prime. So this thing is equal to 1 over v, and then v over 2 pi to the d times the integral d dk, and then times x pi I of k dotted with r minus r prime. Now you can see that the v's cancel out, and so what I end up with is 1 over 2 pi to the d, the integral dk over all space e to the I k dot r minus r prime, and that is the integral representation of the delta function. So this thing is just equal to delta of r minus r prime, and that's true because what we needed was, we concluded from the resolution of unity over here on the left-hand side that it equals delta of r minus r prime, and now I've just gone and proved to you that that is indeed what it is. Okay, so what we've worked out is that there's one point, one state in K space, and it occupies 2 pi over L cubed of volume in K space. And so dk is equal to 2 pi over L to the dn. So that's how you convert from sums into integrals to first order. Okay, there's corrections to this, in fact, but this is the thing. All right, so now that we've done this, now let's have a look at our effective Hamiltonian. So after this little exercise, what we are trying to evaluate is the path integral, the functional integral of this effective Hamiltonian. But now I'm going to write the effective Hamiltonian in K space. So we saw back here on the bottom of the page, here is our effective Hamiltonian in the Gaussian model. We're throwing away the quartic terms because we think we're above 4 dimensions, so we don't need them, they go to 0. And I've written that Hamiltonian in K space. So I do the Fourier transform, and what I get is I get 1 over v, the sum of naught is less than k is less than lambda. And then I have here 1/2 the Fourier components squared, and then their times are naught plus k squared. So that's the Hamiltonian expressed in Fourier components. What I've done is write this on the left-hand side, look on the left-hand side, grad s squared, my Fourier transform, it just gives me k squared times s squared, and then r naught times s squared just gives me s squared as well. So the Hamiltonian for the Gaussian model is completely diagonal in K space, and that makes it extremely easy to do the partition function. Okay, so let's go ahead and do it. So the thing we're trying to calculate then is the partition function is the trace over my coarse-grained order parameter times e to the minus the effective Hamiltonian. And so this trace now goes into a trace not over S of R, but a trace over the Fourier components, S of K. And if I'm going to sum over all the values of the Fourier components, then what I have to do is do an integral. So I'm going to do an integral now over all the Fourier components, going from naught is less than K is less than lambda. And then I'm going to integrate ds of K like that. I'm going to go, S is now the variable of integration. K is just a label. And then e to the minus the effective Hamiltonian of S of K. So remember here that space is just a label. And so K space is just a label too. So this field is labeled by the K value. And then when we say the integral goes from minus infinity to plus infinity, we mean that the values of S, so you tell me what K is. So K is 137. Okay, so S 137, I vary it from minus infinity to plus infinity, e to the minus whatever the Hamiltonian is, and I do that integral. Okay. So that is the problem. And what is on the left-hand side here? Well, this thing on the left-hand side is the partition function. And you might say, well, what is it the partition function of? Well, the only thing it depends upon is R naught, right? Because we have R naught down here on the left in the effective Hamiltonian. So the partition function, after I've done all the integration out of the Fourier components of the order parameter, I will have a function of R naught. Okay, so that's what we're going to do. So now let's talk about the analog of the block spin transformation. So what we're going to do is we're going to define, we're going to be coarse graining by a factor L, just like we were doing before. So now what we're going to do is we're going to say, I've got this whole band of wave vectors that go from here to here. And now what I want to do, so I can think of this as being like this. So here is K, here is 0, here is let's say lambda. And what we want is we want to know what is the effective long wavelength degrees of freedom. We want to know what is the long wavelength effective theory. That's what we want to do. So what we're going to do is we're going to do what Marie Kondo told us to do. We're going to take these Fourier components here, which do not spark joy, and we're going to discard these. So I'm going to say that this scale here, we'll say is set by lambda over L. And so what we're going to do is these ones here do not spark joy. So we discard them, which means we integrate them out. So that is the strategy. So the Fourier variables that are in here, the Fourier variables that live inside here, these are going to be the sigmas that we had before. Remember, we had this short wavelength degrees of freedom, which we call sigma in real space. So these are going to be the sigmas, and these are going to be the SL primes over here. Okay, so that's going to be the analogy, and what we want is the long wavelength degrees of freedom. All right. So so the there's a problem. So the problem is this: when we did when we did the real space version, I had that sneaky projection operator. So we started off with SI as plus or minus 1. We did some RG transformation that I defined, which we used majority rule. And then I got my coarse-grained block spin variables, and they were also defined to be plus or minus 1. Okay, so that was great. And we did that by carefully constructing our projection operator. So what's going to happen here? So here, how do we change the normalization of S of R as we do this process, as we do the coarse grain? So we're going to have to renormalize the magnitude of the spin variable. So what we're going to do is we will literally renormalize the spin variable S of R, or its Fourier components, so that after scale transformation, and then rescaling of space, we get a Hamiltonian, we get an effective Hamiltonian that looks like the original one. And from that, then we can read off the normalization group recursion relations. Now, you probably already realize, so when we did this in real space, here's what we did. We started off with a lattice, we grouped the spins into blocks, we've worked out what is the Hamiltonian of the block spins. Then we rescaled the lattice back so that now we looked at the block spins, and that lattice is just our original lattice. So we're going to be doing this here. We've rescaled out Fourier components between lambda over L and lambda, but we want to have a theory effectively defined from naught to lambda. So we're going to have to make a scale transformation on space. And when we make a scale transformation on space, we're also going to have to make a scale transformation on S. Okay, and that's the renormalization, literally changing the normalization of S to do that. And so what this renormalization is going to be, in this particular case, our renormalization, what it's going to be is that the coefficient of the grad S squared term, let me write it like this, the coefficient of the grad S squared after the rescaling and the coarse graining is always equal to 1/2. So that's going to be a way that we normalize things. And it's going to be kind of interesting, because what we're going to do is if we've now got we've integrated out lambda over L is less than K is less than lambda, so that means that now naught goes to less than K is less than lambda over L. It's long wavelength, but in order to get back to the original problem, we need to rescale space. So R prime will go like R over L, something like that. Okay, just like we had before. Okay, now that's going to be non-trivial. Why is it going to be non-trivial? It's going to be non-trivial because the dimensions of space are the dimensions of S are L to the power 1 minus D over 2. And so space you might scale by a factor of L, but the order parameter will scale by a factor of L to the power 1 minus D over 2. So we're going to get all sorts of weird factors of L to strange powers in this, and that's going to be how we get the critical exponents. Okay, so let's go ahead and define our short and long wavelength degrees of freedom. So what I'm going to define is I'm going to call the variables S of k. I'm going to call those S prime of k, where k is between 0 and lambda over L. And I'm going to define sigma L of k to be the sk variables when lambda over L is less than k is less than lambda. So then, why do I do that? Well, if I want to write down my original field S of R, which is my continuous long wavelength coarse grain field, then I can write in Fourier transform space like the following. It's 0 to lambda over L d dk over 2 pi to the d sk e to the I k dot r, and then I have the integral from lambda over L to lambda d dk over 2 pi to the d s of k e to the I k dot r, and then these variables here, let's use this color, these variables here, that's going to be my sigma L of R, and this variable up here, this variable is going to be what I called SL prime of R before. So this is the analog to SI, block spin, and this thing over here is the analog of the sigma i's that we had in our real space. Okay, so now let's write down the effective Hamiltonian. And this is essentially the following. Just plug it into the Fourier transform. So it's the sum over k is less than lambda over L, 1/2 SL prime squared R naught plus k squared plus 1 over V sum over lambda over L is less than k is less than lambda, 1/2 sigma L squared R naught plus k squared. And these are Fourier coefficients. The SL prime and the sigmas are just Fourier coefficients. And so this is the Hamiltonian for the spins, the long wavelength spins, plus the Hamiltonian for the short wavelength degrees of freedom, sigma L of k. So when I write down the partition function, and we're nearly finished here, so when we write down the partition function, this I write down formally as e to the minus effective Hamiltonian integral ds. What that actually means is the integral from pi product over all the k's, which are in the range there's lambda over L, dsL of k. Then product over lambda over L is less than K is less than lambda d sigma L of K. And then the integrand is e to the minus HS minus H sigma. And you can see that everything factorizes. The exponential factorizes, the measure factorizes, and so this is that Z of R naught is equal to ZS times Z of sigma. And this Z of sigma, this is just like the partition function that we had in the real space picture. So this is like what we had, the Z naught of K to the M that we had in our real space RG, and the HS is going to be the thing that we actually calculate. All right, so I'm going to leave it there for today. So next time we will finish this calculation. We've got maybe 5 minutes more to literally do the integrals. All the integrals are just Gaussian integrals, right? Because the variables are S, and it goes to e to the minus S squared. So it's just the integral of e to the minus x squared, which is a Gaussian. We all know how to do that. We learned it on our mother's knee. And so we can do all these calculations exactly. And from that, we can then work out how the effective Hamiltonian scales. Okay, so I'll leave it there, and I will see you on Wednesday.